The James Webb Space Telescope is now at its destination orbit at the L2 Lagrange point and has started its calibration and final tuning using a star in the constellation of Ursa Major called HDO 84406, which will take about 6 months in all to complete. And already the first engineering images it has taken during this process are better than anyone has expected. So in this video, I thought I'd look at just how the James Webb will see the universe and the tech they had to build to enable it to try and find the first galaxies that formed after the Big Bang and the exoplanets around distant stars. This video is sponsored by NordVPN. If you want to keep a low profile out there on the internet, one of the best ways is to use a virtual private network or VPN like NordVPN, which is what I use. A VPN not only hides your computer's real IP address, it also encrypts everything you send over it, making it ideal for mobile apps, because unlike a web browser, you cannot see if a mobile app is using the secure HTTPS protocol. In recent times, and for some, it's become even more important to hide your true location. And with a VPN, you're just a click away from looking like you're in another country or even on the other side of the world. Nord also has features like Auto Connect and Kill Switch, so that should you forget to start it or even accidentally turn off your VPN, you won't reveal your true IP address and location, ideal for when you're accessing geographically locked websites and content. Act now and you can get Nord's 2-year deal plus 1 month extra for free by using the link in the top of the description below, and there's even a 30-day money-back guarantee, so it's risk-free and there's no excuse for not trying it out. As we have said before, the James Webb isn't a replacement for the Hubble, but its successor, building on the discoveries that Hubble made and expanding on an area of research which the Hubble was never really designed to do. And the fact that the James Webb is also 100 times more sensitive than the Hubble. The reason for this is that the Hubble is primarily set to see the universe in visible light like we do, and ultraviolet, which is outside of our visual range. But to see the very oldest objects, we need to see at the other end of the light spectrum, infrared. This is because since the first stars and galaxies formed over 13 billion years ago, the universe and space itself has been expanding and stretching, so much so that the light from those first stars and galaxies, which was in the visible spectrum, is now in the infrared spectrum. Although Hubble can see some infrared, it is limited, and in its position close to the Earth, very much of this very, very faint early light is lost in the ambient infrared radiation from the Earth itself and the Hubble Space Telescope, as it orbits the Earth and goes into and out of the shade of the Earth 15 times a day. So, placing the James Webb 1.5 million kilometers from Earth in an orbit that also keeps it in line with the Earth, not only do we cut the infrared pollution, but it also keeps us in constant contact with it. To further keep stray infrared from the sun to a minimum, it uses a 5-layer solar shield, the size of a tennis court. All of this to keep the camera sensors as cold as possible, because heat is also in the infrared spectrum. We can't see infrared, but we can feel it as heat. Before we look at the camera sensors, let's go back to the main mirror, a technological achievement like no other made so far. This 18-segment mirror has to do the job that would normally be done by one perfectly ground piece of glass, like that of the Hubble, although as we know there was an error during Hubble's manufacture which meant that the glass was ground to the wrong shape, which effectively made it short-sighted, and another mission was required to fix the error with a set of corrective optics, like giving it a pair of glasses. The James Webb couldn't use this single mirror approach because at 6.5 meters in diameter, the size which was determined to be the best to collect the tiny amounts of its ancient light, the glass required would be not only too big to fit on the launch vehicle, but also too heavy and risk damage from its own weight during its transport and launch. To make up the mirror, 18 smaller hexagonal segments are aligned to focus onto a secondary mirror, which then focuses onto the instruments. Each one of these is shaped so that when all the segments are aligned, it works like one large, perfect mirror. The hexagonal shape for each segment means that there are only 3 optical prescriptions required for the 18 segments, known as the A, B and C segments, and when unfolded there are no gaps between them. Even though the James Webb mirror has over 6 times the light gathering ability of the Hubble, it weighs just 1/10 of Hubble's glass mirror. Each segment is made from beryllium, a lightweight metal that is very strong and good at holding its shape across a wide temperature range and is also non-magnetic. Each segment starts off as a hexagonal blank of beryllium 1.32 meters in diameter, which is then sliced in two to make 2 segments. Most of that material is then machined away from one side to leave support ribs about 1 millimeter thick. This makes the segments much lighter at just 20 kilograms each, but also still strong enough to hold their shape. The segments are then polished to be almost perfect before being sent off for X-ray testing at minus 240 degrees Celsius to simulate being in deep space. Using the data from the tests, the mirrors are sent back for final polishing that allows for the changes in the shape as the temperature drops, and with a surface error or bumpiness of no more than 20 nanometers. The polished surface is then coated in pure gold, which helps in reflecting infrared. This is done by placing the segment in a vacuum and depositing vaporized gold onto the surface to a thickness of 100 nanometers. Because the gold coating is very soft, a final coating of amorphous silicon dioxide or glass is applied to protect it from scratches or particles that might settle and move around. They then go back for one more shape test at cryogenic temperatures. Each of the primary mirror segments and the secondary mirror can be moved in 6 axes by 3 actuators placed on the back of each segment, and on the primary mirror ones, an extra actuator can also adjust its curvature. With each of the actuators in place, the weight of each segment increases to 40 kilograms. Once in orbit, the telescope is pointed at the test star, HD 84406, and the NIRCam, or the near-infrared camera, takes out-of-focus images from each of the 18 segments and then uses computer algorithms to determine how each of the segments must be moved to achieve the correct shape for the whole mirror. Each of the mirrors has to be aligned to with an accuracy of 1/10,000th of the diameter of a human hair to make all 18 segments work as one super accurate mirror. This is done with a subsystem called the Wavefront Sensing and Control, which is responsible for sensing and correcting any errors in the telescope's optics. The reflected image is focused onto the secondary mirror, which in turn reflects it onto the instruments that filter the light or spectroscopically disperse it before finally focusing onto the detectors. Even though the main mirror is 6.4 meters across and has 6 times the light gathering ability of Hubble, the amount of light that comes from the very farthest, earliest galaxies is so infinitesimally small that the whole new generation of large area infrared detectors had to be developed that were not only larger in format, but also lower noise and longer lasting than anything used before. The James Webb uses 2 different types of detectors. The first is the H2RG, made by Teledyne Imaging Systems, and works in the near-infrared 0.6 to 5 micrometer wavelength range. Each one of these is made from mercury-cadmium telluride and has about 4 million pixels. In all, there are 15 of these detectors used by 3 of the 4 instruments on board. Some are arranged in blocks of 4, as you can see here. The cross in the front is the optical baffle, which covers the join between the detectors to stop reflections from bouncing off the edges of the H2RGs. The fourth is the MIRI, or the mid-infrared instrument. This works in the mid-infrared range of 5 to 28 micrometers and is made from arsenic-doped silicon by Raytheon Vision Systems and has just over 1 megapixels. 3 of these detectors are used in the MIRI instrument. The H2RG detectors use a feature of cadmium telluride and mercury telluride in that they are the only common materials that are tunable to detect both very short wavelength IR and very long wavelength IR in one device. The ratio of mercury to cadmium determines the wavelengths that they are sensitive to. However, to work correctly and keep the noise to a minimum, they have to work at cryogenic temperatures. And the longer the wavelength of infrared light, the colder they need to be. For the H2RG, 37 Kelvin or minus 230 degrees Celsius is the ideal temperature, and in the space where the James Webb is, it requires just passive cooling, which is achieved by the 5-layer sunshield. But for the MIRI, it needs to work at 7 Kelvin or minus 266 Celsius, which requires an extra cryocooler, basically a fridge, to bring the temperature down to even less than that of deep space around the James Webb. Now, as you may well have experienced, refrigerator pumps can vibrate quite a lot, and this is the last thing they need, as it could shake the assembly and blur the images. So they use a 2-cylinder horizontally opposed piston pump that is so finely tuned and in balance that it creates almost no vibration. Although the James Webb sends back digital images to Earth, the sensors are analog devices that create varying levels of voltage depending upon the IR that falls on them. And as such, the outputs are susceptible to noise and distortion, so they are digitized as soon as possible to lock the image into the digital domain before they are moved around the rest of the systems on board the telescope and sent to Earth. This is done by the sidecar, or System Imaging Digitizing, Enhancing, Controlling and Retrieving ASIC, an ASIC being an application-specific integrated circuit. This amplifies the faint signals from the sensors before converting them with a 16-bit A to D converter and sends the data in packets for further processing and storage before transmission. As well as looking for the first galaxies, the James Webb will also be looking for exoplanets around other star systems. But how will an infrared telescope help with that? Well, the method they use is called the transit method, which looks at the dimming that occurs when a planet passes in front of a star, or its transit. The amount of light that is blocked by the planet is very small, but from that they can work out the size and mass of the planet, as well as the amount of wobble that the planet induces into the star from its gravitational pull. But the one thing that the Webb can do better than any current telescope is when it comes to analysing the atmospheres of the planets that are found. It does this by looking at the infrared light that passes through the planet's atmospheres, looking for the absorption lines that are created by the presence of different molecules in the atmosphere. And the infrared spectrum has the largest amount of these spectral features. Using Webb's superior infrared detectors, we will get the best look at the makeup of a planet's atmosphere and be able to look for telltale signs of life and even advanced civilizations based on what we know of what our atmosphere looks like spectrally. The first images taken by the NIRCam during the testing have shown the test star HD 84406, which is 100 times fainter than can be seen by the human eye, and in the background are an array of dots. Although the star is of little interest, each one of these dots is a galaxy, and this is the first time we've been able to see them, and is proving that the telescope's performance is already exceeding NASA's most optimistic predictions. Soon we will have the best images we have ever had, not only of the early universe, galaxies and exoplanets, but also planets like Mars, asteroids and other objects, when the James Webb, like the Hubble, is turned to look at our own solar system. So I hope you enjoyed the video, and if you did, don't forget to subscribe, thumbs up and share, and remember that Patreon supporters get ad-free videos before they go live on YouTube.